elastic collisions. And as the diagram hints at here, it's actually how we add energy to orbiting probes to get them to have enough energy to escape Earth's gravity and get all the way out to Jupiter, Saturn, and beyond. Okay, so we're talking about elastic collisions here. So a quick reminder, momentum is always conserved for every kind of collision. It doesn't matter whether energy is conserved or not, momentum is always conserved. So this happens in isolated systems where there's no external forces. So a special case of this conservation principle is when both momentum and energy are conserved, and we call these elastic collisions. So generally, elastic collisions take place between things that are very stiff, hard, like two iron balls in a Newton's cradle, or a very stiff object smacking into a hard floor, or even perhaps two objects with magnets banging against each other. So here's kind of an animation of what's going on. Here we have a 0.5 kilogram block, and it's going to move to the right. And in the first collision, it's going to hit and it's going to stick to the blue block, which is 2 kilograms. So this is what we're used to, a hit and stick collision, like if there's Velcro there. And in that case, energy is definitely not conserved. But what if the two objects were stiff or there was magnets between them? Then one would bounce off the other and would rebound. And this is the problem we're trying to solve. What if both momentum and energy were conserved? What would that mean? So that's the kind of collision we're gonna look at today. Okay? Okay. So here's the problem we're gonna try to solve. A 0.5 kilogram car is rolling along at 3 meters per second to the right, and it's going to collide into a 2 kilogram car, which is 4 times heavier. The collision is elastic, and we want to find the final velocity of each car after the collision. All right. So basically, we've got a car rolling along to the right. These are not drawn to scale, and this one here is a 0.5 kilogram, and this one here is 3 kilograms, so it's a lot heavier. Excuse me, 2 kilograms. It's a lot heavier. So what we are given is that the velocity of car 2 initial is 0. The purple car is at rest. We're given m1, we're given m2, and we know the initial velocity of car number 1. Those are the things we're given. What we're trying to find is the final velocity of car 1 and the final velocity of car 2. So we're looking for two things here. What are their final velocities after the collision? Now you may remember that if the two stick together, their final velocities are the same, and that's what allowed us to solve for it. But in this case, their final velocities might be different, so we can't assume they're the same. So if we apply the principle of conservation of momentum, the momentum after the collision is equal to the momentum before the collision. That means that the product of the masses, so m1 times v1 initial, plus m2 times v2 initial, that's the initial momentum, it's got to equal the final momentum. The problem is we don't know the velocity of 1 final or the velocity of 2 final. There are two unknowns here, and so I can't simply solve this equation for those two variables. I don't have enough information. So here's where it's important to know that the collision is elastic. So if it's an elastic collision, not only is momentum conserved, but energy is conserved also. So the kinetic energy we have before the collision, which is 1/2 m1 v1 initial squared, plus 1/2 m2 times v2 initial squared, that initial energy has got to equal the energy we have at the end, which will be as written here. So here's the beautiful thing. We have two unknowns, but we have two equations. And if we have two equations with two unknowns, we can solve. So our general strategy is going to be to solve one equation for maybe v2 final, and then substitute that into the other equation and eliminate it, and then solve what's left for v1 final. So that's what we're going to do. Okay, so if we look at the momentum equation, P final equals P initial. We've already written this out. Because the initial velocity of car number 2 is 0, this term's going to cancel out and give us this. This is all that remains. And we are trying to solve this for V2 final. We want to find V2 final. So I'm going to subtract M1 V1 final from both sides and then divide by M2. So solving for V2 final, I get the following expression. I don't know V1 final, so I can't evaluate it yet, but I can write it algebraically like this. And I'm going to call this equation 1. And that's what we're going to substitute into our other equation. Now, if you're solving a different problem and the velocity of 2 initial is not 0, you'll just have an extra term here. It's still completely solvable. You'll just have another term here. It won't cancel. All right, so now we have equation 1. We know the kinetic energy is conserved. So that allows us to write this equation. The kinetic energy initial of the car 1 plus the initial kinetic energy of car 2, that sum must be the same as the sum of the energies after the collision. And it's V2 final here that we don't know, and we solved for it. So if I multiply everything by 2 to clear the fraction, because there's no reason to have a 1/2 laying around everywhere, I cancel this term here because velocity 2 initial was 0. And I'm going to substitute in what I got from equation 1 for V2 final. So remember back in equation 1 we solved for V2 final and it was this expression right here. I'm going to substitute that in. So here on the left hand side I have M1 V1 initial squared equals, from here I have M1 V1 final squared, that's that, plus M2 plus this thing right here is V2 final. So I replace that with equation 1 and it's squared. Now, this is an ugly beast, but the nice thing is there's only one variable in this equation we don't know. We don't know V1 final, and that occurs here, and it occurs here. And because this is a rather complex expression, we're going to try to solve this numerically instead of algebraically. It turns out you actually can solve it algebraically, but we're just going to practice some other tools here and solve it numerically. Okay? So to help us solve it, I'm going to substitute in x for the unknown. So this V1 final is my unknown. I'm going to call that x. And then everything else, I'm going to put in my values just so that I can graph it. So what happens is M1 is 0.5, V1 initial is 3, I'll put that in there. M1 is 0.5, that goes there. V1 final squared is my unknown, so I'll put x squared. Plus M2 is 2 times this big expression, which I can plug in everything I know, and of course this V1 final is x, it goes there. So this big old equation is what I'm trying to solve for x, and I know everything except x, so I can solve it. So the easiest way to solve this is going to be as follows. I'm going to graph the left-hand side, and I'm going to graph the right-hand side, and the value of x that makes it true will be where they intersect. So we can solve systems of equations by graphing. These are not linear equations, so you can't use your tools from linear programming from Algebra 2 because this here, x is squared and x is squared here. So they're not linear equations, but they're systems of equations and we can solve them. So I'm going to graph this 0.5 times 3 squared as one graph. I'm going to graph this as the other graph, and then we're looking for the value of x where they intersect. So the easiest way to graph this, you can use your calculator, and it works great if you have a graphing calculator. I'm going to use Desmos. So that's going to look like this. I've already typed in my equations. Here's 0.5 times x squared plus 2 times that parentheses squared. And when I graph that, it's a parabola, and it opens upwards. When I graph the left-hand side of my equation, it's a constant, 0.5 times 3 squared, so I'm graphing the left-hand side here. And that's a straight line, and I'm looking for the intersection points. Now, there's two intersection points because there's two solutions. The first solution I want to point out is right here. So at this point right here, you can see that the solution is x equals 3. We don't really care about y, we care about x. And x equals 3 is one possible solution. But it's what we call the trivial solution, because you may remember that x was the initial velocity, the final velocity of car number 1. And so one possible solution is that x is 3, but the initial velocity of car 1 was 3. And so finding the final velocity being 3 also just means we found one of the solutions, which is what happens when the cars miss. So this is called a trivial solution. It's a way to check the integrity of your solution. If the two cars happen to miss, what would be the final velocity of car 1? Well, it would still be 3 meters per second, and the final velocity of car 2 would be 0 still. So that's the trivial solution. So what we really want, the desired solution, is over here, the other solution. Here x is negative 1.8. So that's what we're looking for. the non-trivial solution to this big old equation is x equals negative 1.8. So you can try it. You can put negative 1.8 in here and plug it all in, and you'll figure out that the left-hand side equals the right-hand side. So that's a solution. Okay? So having solved graphically, we get our solution. Our solution is x equals negative 1.8. And then we have to remember that x stood for the velocity of car 1 final. So we know that the trivial solution is when the final velocity is 3. And the desired solution is when the final velocity is negative 1.8. This is when a collision occurs. Now, using this initial velocity, the final velocity of car 1, we know the final velocity of car 1 is negative 1.8. We can go plug that back into equation 1 to back solve for V2 final. So remember, equation 1 told us that V2 final was this expression here. And we couldn't solve it back then because we didn't know V1 final. But now we know V1 final. It's negative 1.8. So we can plug in all those numbers that we have, mass 1, velocity initial of 1, mass 1, final velocity of 1, and mass 2, and we can arrive at a velocity for car number 2, and it's positive 1.2 meters per second. And so we solved our problem. Our solution is that car 1 rebounds at 1.8 meters per second to the left, that's what's indicated by the negative, and car 2 travels to the right at 1.2 meters per second. So using two equations and applying the principles of momentum and energy, we were able to work through and find the final velocities of both car 1 and car 2. And that's what you're going to do when you solve the next homework assignment, which you can now work on. So this example will be available to you. You can kind of step through it as you need to and see what I did at each step, and then solve those problems.